Welcome to our exploration of systems of particles and rotational motion. In earlier chapters, we focused on the motion of a single particle, treating even extended bodies as if they were point masses. However, real-world objects have size and structure, making the particle model inadequate for many scenarios. This chapter takes us beyond that limitation, introducing the concept of extended bodies as systems of particles. We'll see how the center of mass becomes a key idea, helping us understand the motion of complex objects. By the end of this journey, you'll see how treating bodies as rigid, meaning their shape doesn't change, lets us solve a wide range of problems from spinning wheels to orbiting planets. In daily life, every object we interact with has a finite size. When we analyze their motion, the simple particle model often falls short. That's where the idea of a rigid body comes in, a body with a perfectly definite and unchanging shape. In a rigid body, the distances between all pairs of particles remain constant. Of course, no real object is perfectly rigid, but in many practical situations, deformations are so small that we can ignore them. This allows us to treat wheels, beams, and even planets as rigid bodies for most calculations, simplifying our understanding of their motion. Let's consider the types of motion a rigid body can have. Imagine a rectangular block sliding down an inclined plane. Here, every particle in the block moves together, each with the same velocity at any instant. This is called pure translational motion. Now picture a cylinder rolling down the same plane. While the cylinder shifts position, not all its particles move at the same speed. Some points move faster, some slower, and the point in contact with the plane may even be momentarily at rest. This motion combines translation with something extra: rotation. In pure translational motion, every particle of a rigid body moves with the same velocity at any given instant. This means the orientation of the body doesn't change as it moves. For example, a block sliding down an inclined plane without any rotation is in pure translation. The direction and speed of all points remain identical, and the body's shape and orientation stay constant relative to its path. This concept is fundamental in understanding how forces affect the overall movement of objects. When a solid cylinder rolls down an inclined plane, its motion is more complex than simple translation. Some points on the cylinder move faster than others, and the point touching the plane can even be momentarily at rest. This rolling motion is a combination of translation and rotation. The center of mass of the cylinder moves down the plane, while the body also spins around its axis. This dual nature of rolling motion is common in wheels, balls, and many everyday objects. A rigid body can also rotate about a fixed axis. Think of a ceiling fan or a potter's wheel. In such cases, every particle of the body moves in a circle, with the center of each circle lying on the axis of rotation. The axis itself remains stationary and the motion is purely rotational. This type of motion is seen in many mechanical systems, from spinning tops to rotating machinery, and is a key concept in understanding rotational dynamics. Rotational motion is all around us. Ceiling fans, potter's wheels, and merry-go-rounds are classic examples. In each case, the body rotates about a fixed axis, and every point on the body traces a circular path. The axis of rotation is the line about which the body spins, and understanding this motion helps us analyze everything from household appliances to planetary orbits. Not all rotational motion happens about a fixed axis. Consider a spinning top or an oscillating table fan. In these cases, the axis itself moves, either precessing as with the top or oscillating as with the fan. While the axis always passes through a fixed point, its direction changes over time. These more complex motions are important in understanding gyroscopes, spinning satellites, and many engineering applications. To summarize, a rigid body not fixed in any way can have pure translation or a combination of translation and rotation. If the body is fixed at a point or along a line, it can only rotate. Most real-world motions are combinations, like a rolling wheel, which both translates and rotates. Understanding these distinctions is crucial for analyzing the dynamics of everyday objects. The center of mass is a fundamental concept for understanding the motion of systems of particles. For a simple two-particle system, the center of mass lies along the line joining the two particles, at a position determined by their masses. If the masses are equal, the center of mass is exactly midway between them. For more particles, the center of mass is the mass-weighted average of their positions. This point moves as if all the mass and external forces are concentrated there, greatly simplifying the analysis of motion. For systems with more than two particles, the center of mass is found by taking the sum of each mass times its position and dividing by the total mass. This can be extended to 3 dimensions using coordinates x, y, z. For continuous bodies, we use integrals instead of sums. The center of mass is especially easy to find for objects with symmetry like rods, rings, or spheres, where it coincides with the geometric center. When dealing with real objects made of countless particles, we treat them as continuous mass distributions. We divide the body into tiny elements, sum their contributions, and in the limit use integrals to find the center of mass. For symmetric, homogeneous bodies like rods, disks, or spheres, symmetry tells us the center of mass is at the geometric center. This powerful shortcut saves time in many practical problems. Let's apply these ideas to real examples. For three masses at the corners of an equilateral triangle, the center of mass is found using the coordinates and masses of each point. For a uniform triangular lamina, symmetry shows the center of mass lies at the centroid. Even for more complex shapes like an L-shaped plate, breaking the object into simpler parts and using their centers of mass allows us to find the overall center quickly and accurately. The center of mass isn't just a mathematical point, it moves. The velocity of the center of mass is the total momentum of the system divided by its total mass. Newton's laws apply to the center of mass as if all the mass and external forces were concentrated there. This means that, regardless of internal motions, the center of mass follows the same path a single particle would under the same external forces. If the total external force on a system is zero, the total linear momentum remains constant. This is the law of conservation of momentum. Even if particles inside the system interact, as long as no net external force acts, the center of mass moves at constant velocity. This principle explains phenomena like explosions, where fragments fly apart but the center of mass continues along the original path. In astronomy, binary star systems are a great example of center of mass motion. Two stars orbit their common center of mass, which itself moves in a straight line if no external forces act. In the center of mass frame, the stars move in circles around a fixed point. This separation of motion helps astronomers analyze complex systems with ease. The vector product, or cross product, is a way to combine two vectors to get another vector. Its magnitude is given by the product of the magnitudes of the two vectors and the sine of the angle between them. The direction is perpendicular to the plane containing the two vectors, following the right-hand rule. This operation is crucial in defining quantities like torque and angular momentum in rotational motion. To determine the direction of a cross product, use the right-hand rule. Point your fingers in the direction of the first vector, curl them toward the second, and your thumb points in the direction of the result. This rule is essential for understanding the orientation of torque and angular momentum vectors in rotational systems. In rotational motion, every particle moves in a circle around the axis. The linear velocity of a particle is related to the angular velocity by the formula v equals omega times r, where r is the position vector from the axis to the particle. This relationship shows that the linear velocity is always tangent to the circle traced by the particle, and its magnitude depends on the distance from the axis. Just as linear acceleration is the rate of change of velocity, angular acceleration is the rate of change of angular velocity. It's denoted by alpha and given by alpha equals d omega slash dt. For rotation about a fixed axis, angular acceleration points along the axis, and its magnitude tells us how quickly the rotation is speeding up or slowing down. Torque, also known as the moment of force, is the rotational equivalent of force. It's what causes objects to rotate. Torque depends not just on the magnitude of the force but also on where and how it's applied. The formula for torque is tau equals r times f, where r is the position vector from the axis to the point of force application and f is the force. The direction of torque is given by the right-hand rule. Angular momentum is to rotation what linear momentum is to translation. For a particle, angular momentum L is defined as L equals r times p, where p is the linear momentum. For a system of particles, total angular momentum is the vector sum of each particle's angular momentum. Angular momentum plays a central role in rotational dynamics, especially in conservation laws. There's a direct relationship between torque and angular momentum, mirroring the connection between force and linear momentum. The time rate of change of angular momentum equals the torque, dl/dt equals tau. This means that applying a torque changes the angular momentum, just as a force changes linear momentum. If the total external torque on a system is zero, the total angular momentum remains constant. This is the law of conservation of angular momentum. It explains why a spinning figure skater speeds up when pulling in their arms, or why planets keep rotating unless acted on by an external torque. A rigid body is in mechanical equilibrium when both its total force and total torque are zero. This means it has no linear or angular acceleration. Translational equilibrium requires the vector sum of all forces to be zero, while rotational equilibrium requires the sum of all torques to be zero. These conditions are essential for analyzing structures, machines, and everyday objects at rest. A body can be in translational equilibrium but not rotational equilibrium, or vice versa. For example, a rod with equal and opposite forces at its ends may not move linearly but can still rotate. Conversely, forces can balance rotation but not translation. Understanding these distinctions helps in designing stable structures and mechanisms. A couple consists of two equal and opposite forces acting at different points, creating a pure rotation without translation. Turning a bottle cap or using a wrench are everyday examples of applying a couple. The moment of a couple is independent of the point about which it's calculated, making it a fundamental concept in rotational mechanics. The principle of moment states that for a lever in equilibrium, the sum of clockwise moments equals the sum of counterclockwise moments. This principle is used in seesaws, balances, and many mechanical devices. The mechanical advantage of a lever depends on the ratio of the effort arm to the load arm, allowing small forces to lift heavy loads. The center of gravity, CG, is the point where the total gravitational torque on a body is zero. For small, uniform bodies in a constant gravitational field, the CG coincides with the center of mass. However, for large or non-uniform bodies, the two may differ. The CG can be found experimentally by balancing the object or suspending it from different points. Moment of inertia, I, is the rotational analog of mass. It measures how difficult it is to change the rotational motion of a body. The moment of inertia depends on the mass distribution relative to the axis of rotation. For a system of particles, I equals sigma Ri2, where is the distance from the axis. For continuous bodies, we use integrals. The greater the moment of inertia, the harder it is to spin or stop spinning an object. Let's look at some examples. For a thin ring of mass m and radius r rotating about its center, all mass is at the same distance from the axis, so I equals Mr. 2. For a rod of length L with two masses at its ends rotating about its center, I equals ml2/4. The moment of inertia increases as mass is distributed farther from the axis, making rotation more difficult. The radius of gyration, k, is a useful concept related to moment of inertia. It's defined so that I equals mk2, where m is the total mass. The radius of gyration tells us how far from the axis the mass would need to be concentrated to give the same moment of inertia. For example, for a rod about its center, k equals L/square 12. This concept helps compare different shapes and mass distributions easily. Rotational motion about a fixed axis has its own set of kinematic equations, analogous to those for linear motion. Angular displacement theta, angular velocity omega, and angular acceleration alpha play roles similar to displacement, velocity, and acceleration in translation. For constant angular acceleration, the equations are omega equals omega 0 plus alpha, theta equals theta 0 plus omega 0 t plus a half alpha 2, and omega 2 equals omega 0 2 plus 2 alpha theta, theta 0. These equations allow us to predict rotational motion just as we do with linear motion. Just as work in linear motion is force times displacement, in rotational motion, work is torque times angular displacement, W equals tau theta. The power delivered by a torque is P equals tau omega, where omega is the angular velocity. These relationships are essential for understanding engines, motors, and any system where forces cause rotation. A rotating body has kinetic energy due to its motion. The rotational kinetic energy is given by k equals a half omega 2, where I is the moment of inertia and omega is the angular velocity. This formula mirrors the translational kinetic energy, k a half mv2, and is fundamental in analyzing spinning objects from flywheels to planets. The dynamics of rotational motion are governed by Newton's second law for rotation, tau equals E alpha. This equation tells us that the angular acceleration of a body is directly proportional to the applied torque and inversely proportional to its moment of inertia. This law is the foundation for understanding how forces cause rotational motion in machines, vehicles, and natural systems. For a rigid body rotating about a fixed axis, the angular momentum L is given by L equals E omega, where I is the moment of inertia and omega is the angular velocity. For symmetric bodies, L points along the axis of rotation. This relationship is central to understanding conservation of angular momentum in spinning systems. The conservation of angular momentum explains many real-life phenomena. When a spinning figure skater pulls in their arms, their moment of inertia decreases, so their angular velocity increases to keep L constant. The same principle applies to acrobats, divers, and even rotating planets. This law is a powerful tool for analyzing rotational systems where no external torque acts. Let's recap the key ideas. Rigid bodies can have translational and rotational motion. The center of mass simplifies the analysis of complex systems. Torque and angular momentum are central to rotational dynamics, and their conservation laws explain many natural and engineered phenomena. The moment of inertia measures rotational inertia, and the kinematics and dynamics of rotation closely parallel those of translation. Some important points to remember. The motion of the center of mass depends only on external forces, not internal ones. Separating motion into center of mass and motion about the center is a powerful technique. Newton's laws for systems of particles rely on both the second and third laws. The vanishing of total force and total torque are independent conditions. The center of gravity and center of mass coincide only in uniform gravity. Let's apply what we've learned with some practice problems. For example, where is the center of mass of a uniform sphere, cylinder, ring, or cube? Does the center of mass always lie inside the object? Try working through these questions to deepen your understanding of mass distribution and symmetry. Now try problems involving torque and angular momentum. For instance, show that the area of a triangle formed by two vectors is half the magnitude of their cross product. Or analyze the angular momentum of particles moving in parallel lines. These exercises reinforce the mathematical tools and physical concepts essential for mastering rotational motion. Test your understanding of equilibrium with problems on levers and couples. For example, calculate the reactions at supports for a loaded bar or find the mechanical advantage of a lever. These problems help you apply the principles of moments and equilibrium to real-world situations. Finally, tackle problems on rotational kinetic energy and angular momentum. For example, calculate the kinetic energy of a rotating cylinder or analyze how a child's angular speed changes when folding arms on a turntable. These exercises solidify your grasp of rotational dynamics and energy. Congratulations! You've journeyed through the world of systems of particles and rotational motion. From the basics of center of mass to the intricacies of torque, angular momentum, and moment of inertia, you now have a solid foundation for analyzing both simple and complex rotational systems. These concepts are not just academic, they're the key to understanding the motion of everything from spinning toys to the planets themselves. Keep practicing, and you'll master the art of rotational motion.